Hey guys! Alright, so today I'm going to be teaching you how to do another AP Physics C problem, but this problem is going to be from 1974 and it's a second mechanics question. I'll show you the paper, but you can't really see it that well. So I'll read you what we have to do, and I have my own diagram, and then we'll go from there, okay? Alright. The moment of inertia of a uniform solid sphere of mass m and radius r about a diameter is 2/5 mr squared. The sphere is placed on an inclined plane angle theta as shown above and released from rest. First, for A, they want us to determine the minimum coefficient of friction mu between the sphere and the plane with which the sphere will roll down the incline without slipping. Alright, so first is the diagram. Alright, so here's the inclined plane, and we're going to choose positive down as our direction. You can see the sphere, and the normal force is perpendicular to the friction is acting in the upwards direction because the friction is going to be going against the direction of motion, and the weight just goes straight down.
And you see the angle theta. So I drew a free body diagram, if you can see, and we want to start this problem by using force equals mass times acceleration, which is Newton's second law. So, yay, force equals mass times acceleration. Alright, so the forces acting in the x direction, because there's no displacement in the y direction, are going to be the weight minus the friction. There. Alright, but the weight is going to be equal to mg, but since we only want the horizontal component of the weight, we have to sine theta it. And so we have mg sine theta minus, and the friction force is going to be equal to mu times the normal force, but the normal force, we again only want the horizontal component, so the normal force is going to be mg cosine theta. Alright, so we have mg sine theta minus mu mg cosine theta. And don't forget, this is going to be equal to the mass times the acceleration because it's the sum of the forces. Alright, so since there's an m in each term, we can cancel that out. And so we're going to have acceleration is equal to g times sine theta minus mu cosine theta. Can you see? Alright, so for the acceleration. Now we're just going to hold on to this and we'll use it later. So now to find the mu, we're going to do the sum of the torques. So the sum of the torques is equal to the force times the radius, and is also equal to the moment of inertia times the angular acceleration, which is alpha. So here, yeah. The sum of the torques is equal to the force times the radius and is equal to the moment of inertia and alpha, the angular acceleration. Okay. Hold on one second, I'm sorry. Okay, yeah. So we're going to start off with the force times the radius. So we know that the force is going to be equal to friction because that's the only force kind of deciding on what's happening. So we have r, which is the radius, times the force of friction, which is going to be mu mg cosine theta, which is what we had before, right? And sorry, there, mu mg cosine theta. And they told us in the problem that the moment of inertia is going to be equal to 2/5 mr squared. So we can substitute that in for I, so we get 2/5 mr squared. And we know that alpha, which is the angular acceleration, is going to be equal to linear acceleration divided by the radius. So we substitute that in, and we get A over R. Again, both sides have mass, and both sides have the r's, so we can cancel that out. So cancel m, then the r's end up canceling. So you end up with mu
cosine theta is equal to 2/5 a, correct?
There you go. But remember, I told you we were going to hold on to this, and we already found a here. Here. Where's my finger? There. Here. So we're going to substitute this a in now.
So you have mu cosine theta is going to be equal to 2/5 times g times sine theta minus mu cosine theta. There you go. Alright, so that's what we got when we substituted for a. So basically, now what we want to do is we're just going to go ahead and solve for mu right now. Okay, so let's distribute the 2/5 because it'll make our work a lot easier. So you have mu cosine theta is going to be equal to... Oh wait, hold on. 1 second. You still have a g on this side. And so that can cancel with the g. Oh. You still have the g's on this side, so you can cancel it with the g's that we just added in when we substituted the a. So the g's cancel. So now we distribute the 2/5. I'm sorry. So mu cosine theta is going to be equal to 2/5 sine theta minus 2/5 mu cosine theta.
Now we're going to add 2/5 mu cosine theta to both sides so that we can isolate the mu's.
And so then we get 7/5 mu cosine theta is going to be equal to 2/5 sine theta.
2/5 sine theta. Alright, now we're solving for u, so we'll divide both sides by 7/5 cosine theta.
So you have mu is going to be equal to 2/5 sine theta divided by 7/5 cosine theta.
Like that. But, see, the 5's cancel, and sine over cosine is equal to tan.
So, we're going to get mu is equal to 2/7 tan theta.
And that's our answer for A. Yay!
Halfway done. Alright, now part B. Part B asks, if mu were 0, would the speed of the sphere at the bottom be greater, smaller, or the same as in part A? Explain your answer. Okay, so since the sphere is starting from rest and there's no friction, it's not going to be rotating. There's going to be only translational motion. So if mu were 0, no energy would be lost to the work done by friction. And therefore, all the gravitational potential energy at the top of the incline would be completely converted to translational kinetic energy. So there would be more. This implies a greater speed because if the mass remains constant and the kinetic energy increases, then the only thing to increase is the velocity. Alright?